to get this result from that, right? If x is 3, then the 3 would just go in there for x, right? So this is definitely equal to g of x. And this may be a more typical way you're used to dealing with a function, right? This looks like a function in maybe the way that this doesn't feel like a function, but they are the same things, right? And from this, I can certainly find the derivative, right? Here's a function. Let's find its derivative. The derivative of this is going to be the 3's are going to cancel, and I'm going to get x squared. There's no mystery here, because remember, to get this, we took the antiderivative of this, and now when we take the derivative of that, of course, what are we going to end up with? And then all of this stuff, well, that's a constant, right? So that doesn't matter, that goes to 0, right? And that's why this lower bound actually doesn't matter in the fundamental theorem, because when I take the antiderivative and the derivative, it goes away. So notice what we've done here is we've just showed that part 2, if we accept part 2 of the fundamental theorem of calculus, that also proves part 1. Like they're intimately connected. They're really the same things, just kind of in different directions. We could have gone here directly using fundamental theorem part 1, right? Because that's what fundamental theorem part 1 says. If I take the derivative of this thing, I get back the original, the sort of inside function evaluated at x. And that's what we showed here. So you might say, well, why do we even need the fundamental theorem part 1? Well, it's because what if I give you this function? You may not appreciate this function quite yet, but let's try e to the t squared dt. Now, the problem with this function is it doesn't look very challenging, but it turns out this e to the t squared does not have an easy antiderivative or an elementary function antiderivative. Like there are kinds of functions we can write that function as an antiderivative, but not like the functions that you're used to or that I'm used to. So there is really no antiderivative for our purposes for this function. So I can't do this process here because I can't find the capital F. I don't know what the antiderivative is. But that's okay. I don't need to know what the antiderivative is to find the derivative of g, right? Because that's what the fundamental theorem part 1 says, is that like you don't have to actually find the antiderivative and then take the derivative, because you know what's going to happen. You're going to end up right back at your original function, which is e to the x squared. Right? That's what the derivative is going to be in this case. And so what we're really saying is that this thing, it's kind of both parts, right? The integral and the d of t, this is actually an antiderivative. That's really what the fundamental theorem of calculus is saying, is that this expression is an antiderivative, because when I take its derivative, I get back the function. And this is what's kind of amazing about the whole process, because remember, this notation is actually equal to the limit as n goes to infinity of the sum from I equals 1 to n of e to the x of I squared times delta x, right? Where we have the x of I is equal to a plus delta x times I, and the delta x is equal to, b minus a over n. This is the definition of this expression. Doesn't appear to have anything to do with an antiderivative, right? This is adding up rectangles and figuring out what the limit of those sums are. But it turns out that is actually an antiderivative. And since it's an antiderivative, that's why we know what the derivative is. Okay. Any questions about that explanation or thinking? I find students often, for whatever reason, find the part 2 kind of more believable somehow than part 1. And I don't know exactly why that is. It's possibly something how I explain it, or possibly just that this function is confusing to think about, you know, in the first couple times you see it, whereas this is a little more concrete. Right? It's fixed in a way that this one is not. But they really are saying the same things, which is this antiderivative derivative kind of, relationship. So when I think of the functions, right, I think of, you know, my original function I usually call f. And then I think of levels, right? So the derivative of f is f prime. Right, and the derivatives go down this way, but we can also now go back up, right? And so the antiderivative of little f, we often call capital F. I don't know if that's really like a definition, but it's kind of a convention, something that we use to keep track of these layers. If I started f prime and I find its antiderivative, right, I get f. And if I take its derivative, I should get back f prime, right? So you can kind of step up and down this chain of functions, and they're connected to one another. And to kind of make this relationship a little bit more clear, sorry, let's make it more visible here. We introduce the indefinite integral, which we've seen a tiny bit already. The definite integral and indefinite integral sort of sound very similar, and they're related, but they're actually quite different things. The definite integral is this. This one's a little funny because it has a variable upper bound, right? But it still counts as a definite integral. I have these bounds, and I'm looking for the sum of the rectangles between those bounds. That's the definite integral. The indefinite integral is just a symbol for the antiderivative. If you looked at some of the extra videos I added in, they might have just used that symbol immediately without really defining it, which is totally fine. So when I write this, I've got the same integral symbol, but this is an indefinite integral. There are no bounds here. And so that tells me it's not really this problem, it's this problem. Find the antiderivative. The dx here is just to indicate that x is really my variable, right? That this x is the variable that's changing. So when I do this, I get x squared over 2, and anytime we're taking an antiderivative, remember that we don't know that it's x squared over 2. Could be x squared over 2 plus any constant. So this is the answer that I need for that problem. The symbol here is just used because it's pretty convenient, right? Without the symbol, it's a real pain to say, find the antiderivative of, or I have to define this. Excuse me, I have to define this as f or f prime and say find a upper, the previous function or something like this. This antiderivative symbol, this indefinite integral, is really handy. But don't mistake these, right? This, right, from 1 to 2, this is a number. I don't know what it is yet, right? I can figure it out a couple different ways, actually. I could figure this one out in all 3 different ways, using the definition, using geometry, or using the fundamental theorem of calculus. Right? All 3 of those are options, and they're all going to give me the same value, whatever number this is. This is a whole series of functions, right? X squared over 2 plus different constants. So like the answers there are totally dissimilar things, right? They're not even barely related to one another. Okay. Now, the confusion sometimes comes because a lot of times, actually all the time from here on out, we would like to solve this using the fundamental theorem of calculus. And to do the fundamental theorem of calculus, I have to know the antiderivative. So I kind of need to do this in order to complete this using the fundamental theorem. So, what we would do is we would write it like this to say, okay, well, I know the antiderivative. I'm going to pick c equals 0, which is going to give me this expression. I'm going to plug in 2 there. And I'm going to plug in 1 there. And I'm going to end up with 3/2. So that's how I would expect everyone to solve that problem. But you have to understand what you're being asked to do. If I said geometry, well, in that case, I'm looking at this area. This is y equals x between 1 and 2. And you can see from basic geometry here, right, that that's 1 and that's 1/2. So 1 plus 1/2, no surprise there, right? That's also 3/2. So this is the fundamental theorem of calculus. It's really part 2 if you want to be. This is geometry. And then we also have the definition, right? And the definition is where we figure out delta x and x sub I and then we use this limit of the sum of my function, which is just this 1 plus I over n times 1 over n. And then we have those rules and processes here. Maybe I should do that just as a reminder. This is then the limit of the sum of 1 over n plus I over n squared. The sum of 1 over n is going to be 1 over n times n, because that's a constant. And the sum of I over n squared is going to be 1 over n squared times the sum of the i's, which is n plus 1 over 2. That's a formula. So this is going to be 1 plus n squared plus n over 2n squared. As n goes to infinity, that becomes 1 plus 1/2. 3/2. Sorry, I kind of blazed through that. I didn't want to spend too much time on going back to that. But I think this is nice to see that all 3 of these are equivalent. They always will be. However, geometry is very limited, right? I'm very lucky if I can do triangles and circles. And the definition is also pretty limited. We just don't have the algebraic tools to do much more than x cubed polynomial. This, however, is only limited by our antiderivative skills. So if we can find the antiderivative, the rest of it is cake, easy. So that's going to be our focus here in 5.4 and 5.5 is improving our antiderivative skills so we can use this fundamental theorem for more and more problems. If you continue on in Calc 2, you will spend the first, I don't know, quarter to third of the course learning more antiderivative rules, more strategies for finding antiderivatives. Unfortunately, it is not as easy as derivatives. And you might be thinking, well, I didn't think derivatives were very easy. And that's sort of true. But once you get the rule for derivatives, you can apply it to all the derivatives kind of equally. But with integrals, any little change in the function can make the problem radically different, right? It can become a totally different kind of function. For instance, what if I say the antiderivative of 1 over 1 plus x squared? This one you should recognize as one of our antiderivative rules. Anybody remember what that one is? It's sort of a funny one. It's like not one we see all the time. Yes, that's it. Arctan. Exactly. So this is arctangent of x plus c. On the other hand, if I write it this function, you know, obviously the 2x is something different, right? I mean, that changes it. It's not the same function, but all of a sudden the antiderivative here, and we don't necessarily have the skills yet. We'll learn them in 5.5, but this becomes the natural log of 1 plus x squared plus c. So, right, and you can check that by the derivative, right? The derivative of 1 plus x squared is 2x over 1 plus x squared. So if the derivative works, then you got it. Right. So notice one of these turns out to be an inverse trig function. The other one turns out to be a logarithm function. On the surface, if you just glance at them, they seem somewhat similar, at least to me, a little bit similar, but they're not. Right? And their derivatives and antiderivatives don't have anything in common. So it's just a little illustration of how it's not always clear from looking at it what your antiderivative will be. It's more of an art form than a hard and fast strict rules. Okay. Okay. Questions? Any questions on any of those parts I went over?
I have one question.
Yeah.
This in red pen, you have written like capital F of X and regular, like small f of X.
Yeah.
Yeah, what is this capital F of X is? I thought this like original function is f of X. I don't, yeah, it just confused me.
Well, what I was trying to illustrate there is that if we imagine, and you can start anywhere, there's no reason to think of, you know, whatever function you're given, you could think of it as f prime of some other function, but normally we would think of the original function that we're given as f. And then the idea here is that we can organize our kind of derivatives and antiderivatives in like a kind of list. So if I find the antiderivative here, right, the antiderivative of little f is going to equal capital F. That's the notation that we commonly use for an antiderivative, is capital letters for the functions. It's not a rule necessarily, like maybe if you studied it in a different language, they might use some other symbol for that or notation, but it's common. In the same way, we can think of, the derivative kind of moving us down and the antiderivative moving us up. So that's all this was trying to illustrate here with this.
Sure. Okay. Thank you.
Yeah, you're welcome. Any other questions at all here? Okay. Let me show you just kind of a couple rules here. So this is from the book, obviously, because I'm showing you the book. And these, we've actually, you may have seen these already when you looked in the antiderivative section. These are just the sort of tables, they say, of indefinite integrals, but that's the same as antiderivatives, right? And so some of these we've used already, right? The antiderivative of x to the n here, right? Oh, sorry, x to the n is equal to x to the n plus 1 over n plus 1 plus c, right? That's the kind of power rule, and e to the x and these signs. So a lot of these we already know, but some of them you might be a little less familiar with. And, a couple of them, like here, the arctangent one, like I said, when we did antiderivatives, that one comes up quite a bit. You don't have to worry about these hyperbolic trig functions. I don't cover those. They're not worth our time. This one also, we just don't see that one enough to make it worthwhile. But the rest of them are all just derivative rules. And so they're the reverse of those derivative rules. I would say probably, I don't know where the log one is. They just have this one. That's probably a one to memorize. It was like a not very common derivative rule. It does come up some with antiderivatives. It's our exponential function rule. So these are like kind of our building blocks for these antiderivatives. Again, just look, antiderivative of secant squared is tangent. And we know that because the derivative of tangent is secant squared, but sometimes we don't see it the same way or recognize it when we look at it in reverse. So this is helpful to look at these and remember kind of how that relationship works. Okay. Let's look at just an example here of an indefinite integral. Kind of some strategies of how we can attack those indefinite integrals. Let's look at, I do kind of like this one, the integral of cosine of theta over sine squared of theta. It's from the book too, but I like doing this one as well because the thought process that we're trying to generate here is that when you see one of these, you kind of try some things and know what to work towards. And so the first thing would be to say, number one, I call it like direct formula, which would be saying, okay, is there any function whose derivative is exactly cosine of theta over sine squared? And there isn't. But like if it was secant squared, right, then that would be a direct formula because it'd say, oh yeah, derivative of tangent, secant squared, I'm done, move on to the next problem, right? So we always want to look for that. Sometimes things look They don't look immediately like they might be one, but if we think for a second, we might find that. So that's a good thing to kind of a first step is just to say, okay, anything that this derivative looks exactly like that? If not, then I move on. And the next step here is to simplify. And simplify, maybe I'll put it in quotes because it's like it's not always clear how making it simpler will make it better. We're trying to simplify it for an antiderivative, and when you're just starting out with antiderivatives, you don't always even know what is a simpler form than others. Typically a sum is simpler than a product because of the way derivatives work. That's one good rule. But I'm trying to kind of rearrange it or look at it differently so that I can hopefully see what the formula might be. So in this case, I've got cosine and sine squared here. Do not, before I get started here, do not make the error of saying, oh, I know what the antiderivative of cosine and I know what the antiderivative of sine is, so I can just take those. That will not work. There's two big problems here. One, you've got division, and two, you've got a power. So this is much more complicated than that. Because of the way derivatives work, right? You can't just take the derivative of the top and the bottom and then take the antiderivative of the top and the bottom. You have this whole product rule and quotient rule and chain rule, all this stuff. Those are hard to unravel, right? That's what the antiderivative is trying to do. So we can't just treat each piece separately because this one is divided, right? If it was added, that might give us a chance, but it's not. So one thing that's nice to remember or think about when you've got something like sine squared, right, is just to say, well, it's sine times sine. And then, here we can think of this as two fractions multiplied together. Cosine over sine is what? Anybody remember? Probably do. Cotangent. Exactly. Thank you. See, this is where it would be nice to be in class, right? Because it's like by the time you unmute yourself and jump in, I've moved on too quickly. So normally we don't like to go this direction because we don't really like cotangent and cosecant. But in this case, it's pretty nice because now you may remember that this is a derivative rule. So from the simplification, we put us into our direct formula situation here. Cotangent, cosecant, the derivative of, and maybe you got to look that up, but the derivative of cosecant is negative cotangent cosecant, so I just can put a negative in the front there. Constants are easy to adjust, mostly, right? I can just multiply or divide by any constant I want. It's not going to change like the structure of that derivative. And then again, we're always checking our work. So I say, okay, does that work? Well, if I take the derivative of this, yes, I will get that. So, the example here is that when you look at this, you don't know how to see it, right? But we want to start by recognizing what you can't do and then learning some strategies to kind of change and give yourself a chance to see it, right? So that's really what we're at this stage in 5.4. When we get to 5.5, we'll learn another rule called the substitution rule. And that substitution rule undoes the chain rule. So it turns out the chain rule is actually the easiest one to unravel. The product rule is harder. You'll learn that in Calc 2. So I can write it in here, but we don't know this one yet. Substitution. Otherwise, like some of the same strategies hold when we did the when we learned derivatives, we did some of the same things. We said, oh, this, I can't just take the antiderivative or the derivative, the top and bottom, but I can simplify it first. And it turns out that's good for us for two reasons. One is I can, because of the sum here, I can just take the antiderivative of both of those pieces separately, and that's an improvement. The antiderivative of x is x squared over 2. And 2 over x, that 2 there is, you know, maybe a distraction or something. You can kind of pull it out and take the antiderivative of 1 over x. That's not a power rule, that's natural log of x. So that's one to watch out for. And then always remember your plus c. You might be saying, well, I sort of took 2 antiderivatives here. Do I get a c for both of those? If you wanted to, you could call it C1 and C2, but it's easiest to just combine those together and just give yourself one C to work with, right? C can be any constant you want, so no need to keep separate constants. As always, I like to mentally, like I'm just looking at that and I'm thinking, okay, let me check my work, and I take my derivative. Okay, that works. We always want to do that so that we don't make a little error. Okay. Questions? You know, just like learning derivatives, it just takes a little time and practice, and you will get much better with practice. So don't shy away from trying things here. And if it fails, go back and try something else. It's totally fine. It's a good process, right? Maybe normally in math you don't like to do that, but here you're gonna learn some things about when I take the derivative and I get something totally different than what I started. I'm going to start to recognize like, oh, okay, I kind of forgot how that rule works, or different things. So get some practice on this. And I have posted the lecture captures as they are. Still that little screen. I'm hoping to get into my office this week and try and adjust those and make them more usable for you, but they are posted at least. So I think there are ways of zooming in on that as you look at them. So hopefully that works. And otherwise, schedule wise, you have